All right, so this is the chapter 23 video, the transition metals, chemistry and coordination compounds. And so today's video is going to focus a little bit about the trends in transition metals. And from there, we're going to work our way through until we are kind of getting back to coordination compounds. So these complexes that we can find, that we can form with the transition metals. So remember that your transition metals are basically what we're going to focus on are the D block here. So that means that they're the ones that have D valence electrons. Now, zinc, cadmium, mercury, they are generally considered transition metals, but a lot of what we're going to talk about today and the trends that we see in the chemistries of transition metals, we're not going to talk about with our zinc and our cadmium. And the reason for this is that our zinc and our cadmium, they have complete D subshells. So when you think about zinc, zinc is 4s2 for this electron configuration, 3d10. And so it really doesn't have any more unpaired d electrons to engage in the type of bonding that we would typically see for our transition metals. So a lot of our zinc and our cadmium, we don't see doing quite the same trends that we see with the other transition metals. Now, most of what we're talking about is with the first row of transition metals. These are the trends that you do want to know. As they go across, you can kind of see there's two irregular ones that we want to be aware of. One is our copper, the other one is our chromium. Both of them happen from the benefit of the half-filled D subshell. So they take one of their valence electrons from the 4s and they move it over in order to half-fill their 3D subshell for chromium or to completely fill it for its copper. Now, in general, when we fill our 3D, we fill from the left-hand side to the right. And so we kind of go up in one. So scandium has 3D1, titanium 3D2, vanadium 3D3, and etc. The electronegativity typically increases from left to right. Now, it's not a huge increase in the same way that we see from sodium going on into fluorine or lithium to fluorine. But in general, we do see a little bit of a change here. The standard reduction potential also increases, in which means it's becoming less negative from left to right. So scandium and titanium and vanadium are most negative standard reduction potentials, and that increases. And kind of what's changing with these when we think about them is that their proton count is going up, their relative sizes is staying the same, and so we do see a little bit of an impact there about why their electronegativities, basically effective nuclear charge, is changing. However, that the 3D valence electrons, they seem to do a better shielding job than our S valence electrons, and that's why we don't see as large of a change in their trends in the same way that we would for our main group elements. You can see that our radius also decreases from left to right, which is an impact of us basically adding an electron into that 3D subshell, but increasing our number of protons as well. And so those are our typical trends for our first row transition metals. Now, our first row transition metals, we are all metals in this case, but we do get a variety of different kind of physical properties. Some can be shiny, some can be colored, right? But primarily they're all going to be in the metallic vein of compounds. Now, what I do want you to practice with your transition metals, which is more of a review from Chem 120 or even Chem 119, is we do want to know our electron configurations. We do need to know our irregular ones of our chromium and our zinc for the first row. And so let's try that. Cobalt, we have, we want to know its electron configuration. And so what would the electron configuration for cobalt be? You can see here that I'm giving you the shorthand ones. So make sure that you know or review how to do that. Cobalt is going to be 27 valence electrons. When we look on the periodic table, it's on that fourth period down, so it starts with 4s2, and it has 1, 2, 3, 4, 5, 6, 7 electrons in its D shell, there's 3d7. And then we need to put the argon there as our base core from before it. And so our answer is going to be A, 4s2, 3d7. Now, a follow-up to that might be how many unpaired electrons does each cobalt possess? Now, to remember this, we have to think about the orbital diagrams. So orbital diagrams, 4s for our valence has 1 orbital. Our D has 5. So we talked about this being 4s2, 3d7. So we should put 2 electrons in our 4s. Then we should have 7 in the D, 3, 4, 5. Sorry, that shouldn't be there. And then we need to add our 6 and our 7, so these should pair up. And so when we look at this, we should have each orbital filled before we pair them up. And so we should have a total of 9 valence electrons, or we should have 9 electrons in these orbital diagrams. We have 2 in the 4s. We should have 7 here. So 1, 2, 3, 4, 5, 6, 7. And so we have a total of 3 unpaired electrons. The next part is, let's look at the electron configuration for cobalt. So remember that for our transition metals, the first electrons that we lose are going to be their valence electrons. So we're going to lose their s electrons first. So 4s2 are going to be 2 electrons that we're going to give away for our cobalt. We still need to give away 1 more, so that's going to be 1 of our 3d electrons to give us a total of 3. And so that should be AR 3d6. So if you don't remember these things, you do want to go back and review in your book about the rules for your transition metal, or for your transition metals, and how they gain and lose electrons. You can also review your electron configurations and your Hun rules, Pauli exclusion rules, and the fill from the bottom up. If you're unsure about that, you can always reach out to me. I do have some worksheets, so that way you can practice your electron configurations. Now, our physical properties, we want to think about which ones trend with which ones. So if our atomic radiuses are decreasing from left to right across our transition metals, then we would anticipate that our melting point should, and our boiling points might follow similar trends. However, it doesn't quite stay completely true. Their second ionization energy, or their physical trends, do get some fluctuations. Typically, we see our melting points actually decrease as we go to the right-hand side. Scandium and titanium are 2 exceptions kind of in that round, as well as manganese. We can also watch the same thing with our boiling points. Boiling points typically trend towards the right-hand side, but we do have some exceptions here with our scandium and our titanium and our manganese. And that mirrors their densities as well. So what you can kind of think about is that as our transition metals, they kind of stay relatively the same throughout, but we do get some fluctuation in their physical and their chemical properties. I won't be testing you on their chemical properties and their physical properties, but I do want you to know how their radiuses trend, and more importantly, how their ionization energies trend. So we're looking for our atomic radius for our physical properties, but more importantly than that, we're interested in your ionization energies as well. So our ionization energies for our first one, let me go ahead and erase this one. Our ionization energies for our general trend is our first ionization energy is lower than our second, which is lower than our third, which is typically what we expect. We can also see where our, that in general, we kind of trend from the left-hand side to the right-hand side in our ionization energy increases, right? You see it a lot more in our second, but scandium typically has a lower ionization energy than something, say, like copper, right? And so we do want to know that part. The other trend that we're trying to keep track of is our oxidation states, and we are interested in our most stable ones. So our oxidation states should kind of peak in the middle. Manganese is going to have our highest oxidation number that's available. And manganese is kind of our halfway point. Manganese is 4s2, 3d5. And so it's got the most number of electrons that we can have kind of in this range. We can give away 2 electrons from the 4s2 plus 5 more from the 3d, which is where our plus 7 comes from. Our trend typically increases as we go across 3, 4, 5, 6, 7. And then after that, we typically stay at our plus 3, and then we move on to our plus 2, and then our plus 1 as we move farther right. And so looking at your oxidation numbers, we do want to know in general how that trend kind of follows as we work through our transition metals. And so if we're closer to the middle, we do have the higher oxidation numbers available to us. You can kind of think that they are all of our unpaired electrons, which makes them a little bit easier for us to access. And the second part is when you're looking at these, we do have multiple oxidation states that you can keep. Right? Manganese does have several available. Iron has 2 very common ones, plus 2 and plus 3. And so while we do have all of those oxidation numbers available, you do want to think about that there are options for that. So when we start to go through and do our naming, we do have to remember our Roman numerals. And how that ties in with our oxidation numbers. So let's practice a little bit with our trends. For our element, which one is going to have the largest bonding atomic radius? So looking at our 3 options, they're all in our, well, 2 of them are in the first ionization energy. The gold is in, 2 of them are in our first row of transition metals. Our gold is in our third. So when we think about our atomic radius, period 4 is definitely going to be our shorter one. And we can kind of see that here. Our atomic radius kind of increases as we add on more periods. And so if we're looking for our largest one, our scandium, it's going to be over here on our left-hand side. Now, as we go to the right, we do see a decrease in our atomic radius, and so, or atomic bonding radius. And so that does start to bring things down for us until we get kind of into that copper and that zinc range over on the very far right-hand side. So when we're looking at our atomic radius, if we look at where our scandium should be, this is scandium here. If we look at where our iron should be, our iron is going to be right here. And our gold is going to be over here as well. So our largest atomic radius is going to be our scandium. So this is a little bit different than when we look at our other trends, when we're looking at going down the period. If they're directly above each other, then it makes that comparison a little bit more useful. But really the left to right trend dominates when we talk about transition metals. Okay. So we're looking for scandium there. Let's look at our titanium 5+. Why do we not have titanium 5+? And the good way to start with that one is looking at your electron configuration. So your electron configuration for titanium is going to be argon, 4s2, 3d2. And so if we think about 5+, its electron configuration would actually drop down the whole core level, neon, 3s2, 3p5. And so that requires a lot of energy for us to remove that 5th electron. And so It's not that electron affinity is too large or the ionization is too small. And it's definitely not about it not being stable enough. It's really about the amount of energy required. And so the difference between Ti and Ti5 plus is that we have to remove that core electron, and that is just too much energy to remove it. Okay. Now, our compounds here, our transition metals, what we are most interested in is that they can form what we call a coordination compound, which is going to be a complex ion, and then the counter ions to kind of balance out those charges. Now, a complex ion, what's special about them is that they have that central metal cation, and then is bonded to one or more molecules. So these aren't individual atoms per se all around it, but we can have an atom, plus we could also have molecules. And those molecules or ions are called ligands. Now, how this works is really a Lewis acid, Lewis base bond. And so the ligand has at least one unshared pair of valence electrons. That's what's going to be making this connection to our metal. So if you imagine it, the reaction between the metal and the ligand in the reaction is between the Lewis acid, which is the metal, and the Lewis base, the ligand. So the Lewis base is going to use its unpaired electron to kind of attach or attack that Lewis metal in the beginning, in the center. This gives them some really unique properties, such as color, right? But it also gives them different reduction potentials and also other physical properties and chemical properties that can make them very handy for us. So if you look at our possible ligands that we're showing down here, if we have that cobalt in the center, then these two unpaired electrons can reach out to kind of form that attraction because they are slightly negative and this is slightly positive. And so that's what's forming that metal ligand bond, is that Lewis acid, Lewis base attraction of the unpaired or the lone pair of valence electrons on the ligand to the positive charge of the metal cation. So the metal is going to be our cation. The ligand can be an anion, but it can also be neutral. So overall charge of the complex is simply the sum of all of its parts. So when it's neutral, then our iron must have been a +3, and it has the 6 neutral waters. On the other hand, our chlorine, each of those chloride ions is a -1 charge, and so that's going to be still a iron of +3, but we have 4 chlorides with a -1, and that's where we get this -1 charge for the entire complex. So when we're looking at it, our overall charge here is related to your ligand and it's related to your cation. So we should be able to, we need to memorize the charge of our ligands so that way we can identify what the oxidation state is of our metal cation. So the atom in the ligand that's bounded directly to the metal atom, that's the donor atom. And so a lot of times that's going to be the one that has that lone pair of electrons that can engage in the Lewis acid, Lewis base bond. So they are the ones with the unshared lone pair. The hydrogens would not be considered donor atoms because they are not donating that lone pair. It's only the ones that are directly engaged with that metal. The number of donor atoms surrounding the central metal atom is the coordination number. And so this is how we're going to be able to identify their general electron geometries, is we're going to look at the number of donor atoms attached to it, because that gives us how many different directions we need to spread our electrons in. So ligands can have one donor atom. It's called monodentate. That's something like water or ammonia or chloride. They could have 2 donor atoms, bidentate. One is an ethylene diamine, which is, I'll show you on the next page. But they can even have 3 or more donor atoms. One of those is called EDTA. It's a very common chelating agent that you use in titrations. We call those polydentate because they have multiple options. So you have mono, bi, poly. Now, poly could stand for 3 or more, so we do want to know, at least for EDTA, how many different donor atoms it can have. So a bidentate ligand gives us 2 options, and you can see the 2 amines here that can reach out. So that one cobalt could be connected, in this case, to 3 of these ligands, which means that that cobalt's really connected to 6 things. So you have 1, 2, 3, 4, 5, 6, which gives it a different shape. Each of those ligands looks like that. EDTA, on the other hand, is huge. EDTA has 2 neutral N atoms and 4 sites of anionic, so negatively charged, oxygen atoms. So when it binds to a metal, it binds 2 with the nitrogens and then 4 with the oxygens. So this one binds a total of 6 positions. So it really wraps around them. So anything that has more than one ligand site is called a chelating agent. Now, many of these chelating agents are really important in kind of biochemistry, right? Because many of these transition metals are vital to human life. We see them in something like hemoglobin, where you have the iron as a central one. But there are even other kinds of larger proteins in different complexes or enzymes that we use. The chelating agents interact with those complex ions, those transition metal ions, to form different complexes, to activate them, or in some cases to shut them down. The porphyrin molecule is the basis for many of these biological metal chelates, right? And it becomes this, what we call a porphyrin ring. So an example of this is the iron in hemoglobin carries O2 and CO2 to the blood. And it contains these different hemi units here. You can see how hemi is kind of tied in with our protein on top or protein on the bottom. And so it's getting chelated there with the these different agents attaching around that iron to kind of open up that iron in order to hold on to that O2. The chlorophylls also uses a porphyrin agent, right? So this is porphyrin up here. So this is the porphyrin section of chlorophyll A. In order to utilize its metal process as well, right? So this interaction between the transition metals, even if it's not at huge concentrations, can have a big impact in biological applications. So let's think about this. Right now we have ammonia, which is NH3, and it's working with a metal cation. Is this a Lewis acid base interaction? And if so, which species acts as the Lewis acid? So this is a ligand and this is a metal, and so that is definitely going to be a Lewis acid base interaction. Now when we think about it, our Lewis acid is going to be the one that accepts the electrons. So the one accepting the electrons is going to be our metal cation, and so that's going to be our Lewis acid. So we're looking for B. Let's think of it this way. Now water and ethylene diamine, so that compound I just showed you, they both have 2 non-bonding pair of electrons. Why can ethylene diamine act as a bidentate ligand, but water can't? So why can the ethylene diamine attach to 2 different sites of the metal, but our water can't? So when we think about the difference between them is that the water molecule, both of its lone pairs are associated with that same oxygen. Since all of its lone pairs are on that one oxygen, then when it attaches to that metal cation, it can only form or count as one donor atom. On the other hand, our ethylene diamine has 2 of those nitrogens with a lone pair. And so our ethylene diamine can form 2 different bonds or metal ligand attractions because its donor atoms, there's 2 of them instead of only being 1. So it's not that the water lacks the nitrogen atom. It's not that there's not enough lone pairs. It's really that both of those lone pairs are stuck on that one oxygen and not spread out. So this is a table that kind of starts to show our different most common ligands. Yeah? And so we do want to know these. We do want to know which ones are mono and which ones are bi and which ones are poly. But you can kind of see here that our mono ones have generally just one atom that has the ability to form that metal with the lone pair on them. A chloride, a cyanide, or thiocyanate, or water. Typically, it's going to be your most electronegative. Typically, it's your most electronegative atom. That is going to be the one to donate its lone pair to connect in with that metal, right? And that's because it's going to have your largest partial negative, right? Compared to the partial positive of your metal. And then down here at the bottom, we can see our EDTA. So we have our 1, 2, oh, sorry, this one. We have 1, 2, 3, 4, 5, 6 for our EDTA. So we do want to remember how many connections EDTA makes because EDTA is one of those so common ones. So we've talked about our oxidation number. The other one that we need to talk about is our coordination number. So our oxidation number comes from your charge. So we can backtrack from your total charge minus the charge of your ligand. And that should give us our charge of our metal. Now, if our ligands are negatively charged, then our metal has to become more positive, so we should be minusing a negative charge of that. If our ligands were neutral, then it's a 0, right? And then our total charge is just going to match the charge of our metal. But that's how we can find our oxidation numbers. Our coordination numbers are different. Coordination numbers depend not just on the ligands, but also about their sizes. So sometimes it's about the charge. There's only so much charge the central metal can take, but also the sizes of them. So for an example, iron 3 can bind 6 fluorides, but only 4 chlorides because they're so much bigger. Those 4 chlorides, we can't physically fit the 6 of them around because of their repulsions that they see. Now, our most common coordination numbers are 4 and 6, and they generally take on the tetrahedral geometry or the square planar geometry or an octahedral, depending on which one. Now, what you want to think about is your coordination numbers are very similar to your, or related to your electron geometries. So in the same way that we used to find them based on how many things were connected to them, you can do something similar for this one. When we are looking for your coordination number, all we have to do is tie it in with our number of ligands. So your coordination number is equal to your number of donor atoms. So if you want the equation for that, is take the number of ligands and you multiply each by the number of donor atoms in them. So if we have something like ammonia, this one has one option for it. So we take our number of ammonias times 1, right? If you have ethylene diamine, it's got 2 sites. So you take each of these and multiply it by 2. Our EDTA has 6. So you take each of those and you multiply it by 6. And you add those together. And that will give you your coordination number. So when we think about iron with the 6 fluorides, right, that complex should have a charge of 3 minus because it's got 6 minus 1s, and that iron 3 is a plus 3. And so our iron here has a coordination number of 6. When it only can bond to the 4 chlorides, its charge is a minus 1, and its coordination number is 4 because it has 4 different donor atoms attached to it. Okay. Let's say that cobalt 3 has a coordination number of 6 in all of its complexes. Is the carbonate ion a monodentate or a bidentate ligand in cobalt NH3 CO3 plus? So we can think about this and we should be able to figure this part out. So we know that ammonia has just 1. It's a monodentate ligand. We have 4 of them. So this takes up 4 bonding sites. Our cobalt should be a total of 6. So we take away the 4 from that NH3, and that gives us 2 bonding for our carbonate. And when we look at it, we have 1 carbonate. So that should tell us that we are a bidentate ligand. Now, our second part is if we wanted to look at the charge of that cobalt, our charges should match up in that we know that ammonia is going to be neutral, so that would be a 0. Carbonate is 2 minus, so if we were to look at our charge, we have a +1 minus a -2, so +3, which lines up well with that we are a cobalt 3 as well. Very good. Can the ammonia linking, oh, this is ahead of the game. We're not going to be, I need to move that one back in a second. The second part that we're going to get into today is we're going to talk about our naming. Right? So complex ions, right, or coordination complexes, they get their own naming rules. And so they follow similar to our ionic ones in that the cation is always going to be named first, and then the anion. Now, within the cation or the anion, depending on what charge our coordination complex takes on, we're going to name the ligands before the metal, and we're going to list them in alphabetical order. So we don't care about their charge, we only care about the alphabetical order. The ligands will go first, and then the metal. Now, you know what charge they are because the anionic ligands should all end in the letter O, and the neutral ones just are the name. Now, ammonia and water are exceptions to that. And so we want to be careful with that when we use their names, right? We're not going to do dihydrogen monoxide, we just say water, right? Well, we say aqua. Right? Greek prefixes di, tri, and tetra are used to indicate the number of each kind of ligand. If they already have one of those prefixes in their name, then we use the bis, tris, and tetrakis. And then the ligand name is going to be placed in the parentheses. So that way we can separate those two. If the complex is an anion, then we want to change the metal to end in 8. And then the oxidation number of the metal is given in parentheses in Roman numerals following the name of the metal. So it seems like a lot, but we'll do some examples and walk our way through it. So let's look at this one here. We have sodium, we have molybdenum, and we have OCl4. So the first part is we need to name our cation, which is sodium. So we do that part first. We have our sodium here. And if you were to think about it, this is really a sodium plus an MOOCl4. And each one of those should be a minus 2. And so then when we start to name our complex, we need to name our ligands first. So we have 4 chlorines and we have 1 oxide ligand. So we're doing our 4 chlorines and then our 1 oxide because C comes before O. So we call that 4-chloral, so tetrachloral. Then we have our oxide, which is oxo. Normally we would put molybdenum, but because this is an anion, it's got a -2 charge, then we need to change the ending to 8. No, sorry, you spelled that one wrong. So we change the ending to 8, and then we want to figure out its charge. So if this is a -2, then we have 4 -1s plus a -2 from the oxide. So we had -6 total. We ended up with a -2, so our molybdenum had to be in a +4 state. And so that's how we get that name there. When we look at our next one, we have cobalt and ammonium and chloride. And this is going to be our cation, positive, with 2 of our negative charge chlorines. So that means that we have CO, NH3, 5Cl. All of that has to be a +2. Now ammonia is going to be neutral, 0. Chlorine is going to be -1. And so this tells me that my cobalt has to be a 3+ in its charge. We're comparing our ammonia versus our chlorine. So we're going to name this part first. So we're going to name it our amine. Then we're going to name the chlorine. So there's 5 amines, so that should be pentaamine. 1 chlorine, so chloral. Cobalt, and we can leave the ending there because it's not an anion, and then our number 3. So it should be pentaamine chloral cobalt 3, and then we have the anion chloride. And that's how we can work our way through it. There's some more ones for you to practice here. We have nickel 2 bromide, or sorry, we have nickel 2. It's bonded to 6 amines. It has a 2+ charge because we have a bromide, or we have 2 bromides with a -1 attached to it. This one we already talked about, our sodium. And so then we can do another cobalt one down here. Now, the cobalt one's a kind of interesting one because we have a lot of things going on there. So we have 3 different types of ligands. We have water, which we call aqua in its ligand form. We have CN, which is our cyanide or cyan. And then we have the ethylene diamine. So when we think about them in alphabetical order, then water is going to go first, aqua, then the CN, cyan, or cyano, I guess, because it's ending in the O, or it's the anion. And then we're trying to say that we have two ethylene diamines. And so normally you would think it would be diethylene diamine, but because we already have the di in here, then we have to use the second set, which is our bis, tris, and tetrachus. So we have two of them, so that's going to be our bis, put the parentheses, ethylene diamine, cobalt 3 chloride. So you can start to see why sometimes as we get bigger and bigger in these complexes, they start to come up with abbreviations shorthand, kind of like EDTA, because those names are starting to get very complex and very overwhelming in some cases. I would recommend that you make an attempt to do this one on your own, right? And then afterwards, we have some slides that walk you through it. Now, before you do that part, this is going to be a list of your common ligand names. And so you do want to know these. You want to go ahead and memorize these. If there's one that I give you that's not on this sheet, then I would give you information about them. I would tell you if it's mono. I would tell you if it's an anion or a neutral. Right? But these are the common ones. And so in the same way that your polyatomic ions are more helpful once you start to really know them, I would recommend the same thing for this. In the beginning, keep the list around with you, work your way through. But eventually you're going to want to know these, which will make it much faster as you're going through the naming process. For your metals, I wanted to let you see what it looks like with the anions. The hard part with your anions is that while most of them are just like what you find in the periodic table, there are some exceptions. So things like gold, iron, and lead, silver, and tin. The anionic metals replace the ending in the name with 8, but it's based off of their Latin names. So for your symbols, if your symbol doesn't match up with your metal, then you do want to be checking what their base name is. Now, while these are the ones that I expect you to know, if I gave you one outside of this list, then I would give you what their base name is. So you would want to make sure that you knew how to change that. An example of this is antimony on the periodic table, but the base name that we could use is stibium. So if we wanted to make that an anion, and then you want to make sure that you can practice those as well. So there's kind of two places for you to practice doing your naming. And you want to work your way all the way through. The last part that I want to talk about is going to be isomers. Now, with your complexes, we have a lot of different arrangements that they can take on. So an isomer is something that has the same molecular formula, but it might have a different arrangement of those atoms. And so there's different classifications of what they could be. Structural isomers mean that they have the same molecular formula, but different connection of atoms. Let's say that instead of having carbon, carbon, oxygen, hydrogen, you might have that as carbon, oxygen, carbon, hydrogen. The atoms are not connected in the same way anymore. Those are structural isomers. Stereoisomers means that they are connected in the same way. CCOH, right? The next one is also CCOH. But they have different three-dimensional orientations. That means that when we were to draw them in 3D, they're not going to overlap. And so those are some ways to think about what your different ones are. And so this flowchart down there is supposed to help you clarify them. Inside our structural isomers, we could have different ones. Do the same ligands bind to the metal one? If not, then it's coordination sphere. If it is, then we have linkage isomers, so the linkages are changing. Stereoisomers can get separated by geometry or by optical. So a linkage isomer means that the ligand is bound to a metal by a different atom. For example, nitrite combined with either the nitrogen or the oxygen. So you can kind of look down here. This is our nitrite. The nitrogen has a lone pair and it can bind in there. Or our oxygen has a lone pair and they can bind in there. So both of them would look the same in the molecular formulas, but how they're linked is very different. And you can see that actually produces a physical color change for the compound that we make. A coordination sphere is different in that it's which ligands are bound to the metals and which ones are outside of the sphere. So this would be like if we had metal hydrates. One version has them where our chromium is attached to the waters and then these anions float around outside. In this other one, the waters are attached to the chromium with one of those chlorines and only two of those anions are not attached. So it's attached to that chromium. And then our water is associated on the outside as well. And so there's a couple of different options. So all of them have the same makeup, but they have different ones about who's part of the complex and who's part of that anion or that kind of the supporting charge particle. Stereoisomers are our geometric ones and our optical ones. So that means that everything looks kind of the same about them until we start drawing them out in their 3 dimensions. So they're same chemical bonds. So if you don't have the same atoms bonding to the metal, then it's not going to be a stereoisomer. If you have different atoms connecting to different atoms, they're not going to be stereoisomers. They're going to be some other type of isomer. Geometric ones, they're connected the same way, but they're connected in a different orientation. And the most common one that we talk about is cis and trans. Cis means that the ligands are adjacent to each other. So in this case, it's our chlorine and our chlorine. And you can see that they're next to each other, making this L shape. On the other side, a trans one means that they are opposite of each other. And you can see that this chlorine is across from this chlorine. It makes a straight line going from one to the other instead of that bend or that L. This is very common in our octahedral complexes when we have them kind of in that square planar arrangement. And so they can be either next to each other or they can be across from each other. If you think about it, this angle difference between them is 90 degrees, whereas this one is 180 degrees. They have different physical properties, but they also have different chemical reactivities because of that change as well. So cis and trans can be very different than each other. This is an example of the cis version of our platinum ammonia. So this is, we can practice this. This is going to be our cis. We have no charge up here, so this should be cis diamine, because we have two amines, dichloral, because we have two chlorines, platinum, because it's not a negative charge, and this one should be platinum 2. The cis is telling us that when we have our chlorines in there, that they are next to each other. Our trans is telling us that they're going to be across from each other. Now, both of those complexes, or in this case, this is going to be our cobalt geometric isomers. They both have that same arrangement. So they both look like octahedrals, but you can see that this one forms that L again, whereas this one is going to be trans. And when we visualize this, you can actually see the difference in their colors. One makes a pink compound, the other one makes a green compound because of their arrangement. So one way to think about it is that when you connect them, try to rotate them in your mind. If they rotate to look like the other one, then they're not going to be a geometric isomers. They're just the same thing written in a different way. If they don't ever overlap, then that means that they're going to be a geometric isomer. So let's look at these two here. We're looking at compound C and compound D. We want to see, are they new geometric isomers of our cobalt amine chloral complex. And so when we look at this, we have chlorine and our chlorine. But if we rotate this chlorine down this way, bring it into the same plane, this chlorine would have stayed, this amine would have stayed, and these four would have rotated. You can kind of see that that would remake our A. We would still have this L shape between them. And so that looks a lot like our cis geometric isomer. On this side, if we were to rotate this chlorine to swap with that one and this chlorine to swap with this one, you can see that we would end up in the same arrangement as B in the trans position. Our chlorines are across from each other. You can also imagine that when we look at it, these four are all in the same plane in the same way that these four are in the same plane, and then those chlorines are across from each other. These four are in the same plane as these four, and we still make this L shape just like we do here. So the short answer is no. They are not new geometric isomers. They're the same ones that we had before. We just get them by rotating C to A and D to B. Okay. Now this is an interesting question. Can a trigonal planar complex exhibit geometric isomerism? And so let's think about what you know about a trigonal planar, and then think about, can you come up with a geometry isomer? So trigonal planar means that you have one atom in the middle, you have three different groups that it could attach to on the side. It makes a triangle, they're all in the same plane. And so when we think about it, is there another arrangement that will give us something different? And so if we have two purples and one orange, we could have this arrangement. And if we made another one, we might try to put it like this. But if you were just to keep rotating it, you can rotate it one back this way. You'll see that it looks the same as the one at the left. So it's not an isomer. If we do it in the next position, you can see that if we were to rotate this down, we would get the same one as before as well. So this is also not an isomer. So trigonal planar complexes, they can't exist with the geometric isomer because all the structures are equivalent. No matter what we do, there's no cis and trans because they would look the same. So that's our geometric isomer side. The other part is what we call an optical isomer. So optical isomers mean that they are mirror images of one another, but they don't superimpose. So that means that if you put them on top of each other, they don't look the same. This is also called chirality. So things that are optical isomers are called chiral. Their properties differ from each other, but that only matters if they're involved with other chiral substances. So your best example of this are your two hands. Your two hands have their same arrangement. You wouldn't want to use cis or trans for either one because they're connected in the same way. It's not that they're not next to each other or they're not across from each other. But when you look at it, if you overlap your left hand and your right hand, you can't get them to both be doing the same thing. If you put them on top of each other, their palms are not facing in the same direction. If you lay them up so that their palms face the same direction, then your thumbs don't line up. And so this is what it means to be an optical isomer, is that you are a mirror image of the other one. And so while you're very similar, you're not exactly the same. We can't make one of them look like the other. So if we look at our examples down here at the bottom, we have the cis version and we have the trans version of this cobalt benzodiazepine with the 2 chlorals. You can see that for our trans version, while we've mirrored them across, if we take this one and we rotate this chlorine here and this chlorine there, our molecule ends up looking identical to the one on the left-hand side of the mirror. It means that they are superimposable. So that means that they are not optical isomers, and this is called achiral. It means that they're going to be the same. On the other hand, when we look at our cis version here, if we start to rotate this one over, we're not going to get them to be able to line up in the same way as we could with our trans one. And so they're going to become our optical isomer and be listed as chiral. And you can kind of see why they don't overlap. If you were to look at this chlorine right here, when this chlorine rotates one over, then this one's going to move one back. When it moves a second time over, so that way it's now facing to the back, this one is going to be facing to the front. So instead of being the down facing to the front, it's really the top that we have facing to the front. And so it's not going to directly overlap with the other one. And so that's why this becomes a chiral option, is that our arrangement becomes, our arrangement looks something like this. We have our metal coming over to the forward side. We have our chlorine going back. We have our chlorine coming forward. And then we would have this metal going back. To finish the bottom part. And so that's why they're not considered isomers of each other. Or sorry, they're not considered to be superimposable. Is because one, the top one and the bottom one are not going to be aligned. Now, how you tell optical isomers apart is you put them through what we call the polarized light beam. Right? So what happens is that they rotate plane polarized light. Now, normally a light source sends out light waves that go in all kinds of directions. But if we put a polarizing film, we can kind of arrange them so that they will only travel like a wave in one direction. Now, if we put our compound inside here, we can see whether or not they're going to be rotated one way or the other. Are they rotated right or are they rotated left? If they're rotated right, it's called dextro-rotary, and so it gives an orientation of a D. If they're rotated left, then it's called levo rotary, and they're rotated L. And so this is how we kind of get their names. We call them L or D compounds, depending on which enantiomer we're talking about. If you have both of them mixed together, it's called a race-mix mixture. And it means that overall, half gets rotated one way, half gets rotated the other way, and so we won't see a difference. So they're called optical isomers because so much else remains the same except how they interact with light, which does eventually start to lead to other types of chemistry, especially when they start to interact with other optically active isomers as well. So which of the following physical properties of the D and L enantiomers of a substance are different? The melting point, the way the polarized light is rotated, the color, or all of the above? And what we'll find out is what's going to be different for our optical isomers is just the way that we rotate the light. The other parts remain the same. The color depends on the metal and it depends on the ligand. And so the thing to remember with color is that the two ways we see color in a complex is that either the object reflects that color or it transmits all the colors except the complementary one. What that means is that when we are looking at it, your eye is either seeing the light that bounces off of it. So when we are shining light on an orange, it's not that the orange produces something, it's that the orange reflects just that orange light. On the other side, if we shine a piece of glass, a blue light, a glass that absorbs only blue light, we see as being an orange colored glass. Because all of the other light gets through, but we're missing the orange, and so the opposite of it kind of gets expanded in our peripheral. It doesn't get balanced out, and so we see it as blue. So when we talk about absorption spectra, we're going to see the opposite of that for the solution. So in this mixture up here, our blue, green, and yellow is absorbed. So if blue, green, and yellow is absorbed, then we see a mixture of the violet, red, and orange. Of violet and red. And so that's how we're going to get that purple shading in there. So when we see each of these different spectra, these colors are the complementary color of where they are going to absorb. And so when you want to do your color wheel, the thing that I recommend is Roy G. Biv, red, orange, yellow, green, blue, and I guess there's no indigo. It just goes right into violet. Right? So it's like the color of the rainbows. And so if you take your circle, split it in half, split each of those sides into 6. If you go through and you list them as Roy G. Biv, you should get R, O, Y, G, B, and then our violet. So no I, you don't have to worry about indigo. And that way you can find your complementary colors. We're going to stop there for today. On Wednesday, we're going to get into your coordination complexes. So we're going to deal a little bit more with geometries, and then we're going to talk about their crystal field splitting theory.